il a obtenu son... Il a obtenu son doctorat, so he got his PhD from Georgia Tech. So, and as I said earlier, he's working on computer-assisted proof, or if you like, des calculs vérifiés, ceux qui peuvent être utilisés pour étudier l'existence de bifurcation, de solutions périodiques dans des systèmes dynamiques. So today is going to apply this to the existence of periodic motions and read something that should be of interest to both mathematicians and engineers. So, Jean-Philippe, c'est à toi.
Parfait, merci beaucoup. Merci beaucoup, Yves. Merci beaucoup de l'invitation. Thank you very much for the invitation. So I'm actually giving a talk from Prague in the Czech Republic. I wish I would have been there in person. Anyhow, so thanks a lot for the invitation. So yeah, today I'm going to give a talk about computer-assisted proofs of existence of periodic motions in fluids, and I will try to actually give a more broad talk. I don't want to go too much in details. So I'll discuss, of course, one application to the Navier-Stokes equations, and then I will kind of talk more generally about the techniques, and then I will go back at the end of my talk. I will go back and discuss about the application to Navier-Stokes. Okay, so a little bit of motivation here. So many of you know the Navier-Stokes equations, and here are the equations of motions. U here is the velocity, P is the pressure scaled by the density, nu is the kinematic viscosity, that's going to be an important parameter, and F is acting as an external forcing term. So that's going to be a very important element in this talk, the actual external forcing term. And so as many of you know, of course, there is the famous Millennium Prize problem, which says that in 3 dimensions, given any initial velocity, and a zero forcing term, then there exists a long-term global existence which exists for all time and which is smooth. So that's the famous Millennium Prize problem, and it's posed on the 3 torus. There's a version on the 3 torus, and there's a version, I think, in all of our 3. Okay, so of course this is important. That's a beautiful problem. Lots of interesting mathematics is being developed to understand this problem. But from the dynamical systems perspective, this may not be the most important question. And in fact, yeah, but that's really is from the dynamical systems perspective, of course, from the engineering viewpoint. And then if you want to make, you want to design wings and so on, and you want to use that in the practical setup for the purpose of really using the motions to design something, then that's I mean, you want somehow to know the answer to this question. But from dynamical system perspective, it's not maybe the most important. And in fact, Poincaré himself would say, well, who cares? Who cares about trying to get long-term existence? So the question is, what kind of solutions do we care about? So from the point of view of Poincaré, the real father of modern dynamical systems, then we should investigate bounded solutions. So bounded solutions are what? Bounded solutions are steady states, they're periodic orbits, they are, let's say, connecting orbits. So if you look at this graph here, that would be, say, a phase portrait of, that could be an infinite dimensional phase portrait where you have, say, equilibrium solutions, you have limit cycles. So what is interesting from the viewpoint of dynamics are these bounded solutions. So these asymptotic solutions which exist for all time. And they are particularly interesting because they are very smooth. So they're smoother than, say, a typical solution of an initial value problem, and they're low dimensional. So again, if you take a look at this cartoon picture here, then you could think of each point here as being, say, a solution to a PDE, for instance, or delay equation, and so on. So each point is in an infinite dimensional space, but the actual objects which are bounded are very low dimensional. So an equilibrium is 0 dimensional, a periodic motion is 1 dimensional, limits, I mean, connecting orbits are, this is also 1 dimensional object. So these objects, which are kind of acting as an organizing center for the general dynamics, they're often low dimensional and they're very smooth. And this is a strategy, and this is something these features of low dimensionality and regularity, we will be using them to design our computer-assisted proofs. And from our perspective, what we do is that when we have these objects of interest, these bounded solutions, we reframe them as looking for zeros of nonlinear operators in function spaces. And I'm going to be more explicit about it. Okay, so now I want to talk a bit about what is known regarding existence of periodic motions in Navier-Stokes. And by what is known, I mean really what is proven with pen and paper techniques, like mathematically proven. So in 1959, Seren, he published 2 papers on the existence of some solutions in the limit of the large viscosity. So you can think of the fluid as very, very thick without, the fluid doesn't necessarily want to move. And so he proved that the existence of a globally stable equilibrium solution, we sometimes call this the viscous equilibrium. And he also showed that the existence of periodic solutions on a 3D bounded domain subject to time periodic boundary data and body forces. So it's really important to realize that he proved the existence of periodic motions subject to time periodic boundary forces. Okay, so that basically is a consequence of the fact that the external forcing term is in fact time periodic. And after that, many people followed the work of Seren, the pioneering work of Seren, by studying the periodically forced. And from the viewpoint of dynamics, this is what we call a non-autonomous dynamical system, because there is a term in there which depends on time. And that is the time, the time-dependent forcing term here. So if you think about the Navier-Stokes equation here as a dynamical system, at least for short time, then if F depends on time, explicitly on time, then that's a non-autonomous dynamical system because the forcing term depends on time, right? So many people following the work of Seren, they actually proved the existence of periodic motions based on the fact that the periodic forcing term is time periodic. Okay, so I would say that our understanding of periodic orbits and periodic motions in Navier-Stokes in response to time periodic forcing is rather advanced, but we cannot say the same for forcing terms which are not depending on time, and these are referred to as spontaneous periodic motions. Okay, so by spontaneous periodic motions, I will really mean a periodic motions which arises in Navier-Stokes or in the fluid motions, which is not subject to time-dependent forcing term. Okay, so that's the goal of today's talk, is to focus on these type of objects. So an example of such a spontaneous periodic motion is a famous von Karman example, where you do have, say, a fluid moving on the right, and then you have this cylinder here, and then there is this periodic motion that arises as a consequence of the nonlinearity in Navier-Stokes, and it is not because of a consequence of, say, a time periodic forcing term. Okay, so that would be an example of a spontaneous periodic motion. And if, for instance, you can think of redoing the same experiment, but say with very high viscosity, then maybe nothing would happen. But then if you lower the viscosity, then at some point there will be these spontaneous periodic motions which will appear in this von Karman experiment. So these are the kind of objects that we wish to be able to prove using the tools of computer-assisted proofs. Okay, so that's what I said. So we want to develop a general approach to prove in a mathematically rigorous sense existence of periodic motions, spontaneous periodic motions in Navier-Stokes. Okay, so I am kind of between a pure and applied mathematician, so I really wish to be able to prove things with pen and paper, but that really requires, in my viewpoint, the strength of both worlds of pure and applied math. And in fact, especially for Navier-Stokes, it's so hard because it's an infinite dimensional problem, and the equations, you have the nonlinear terms. So this is a major difficulty. So now I'm going to step out of Navier-Stokes, and I'm going to start asking general questions about how do we study nonlinear equations, and what can we do to actually get our hands on trying to prove theorems about nonlinear equations in general. And I would say that traditionally, there are two main trains of thoughts that have been taken to actually address this. How do we study mathematical equations and nonlinear equations? So there is the tower here that I will call the pen and paper tower, where you have the pen and paper analysis. So in this tower, you have beautiful, powerful mathematical theories that have been developed to study nonlinear equations. And some of them may actually look quite theoretical, like Floer homology. For those of you who know what Floer homology is, this is really an algebraic topological invariant designed to characterize originally the number of periodic motions in Hamiltonian dynamics. So Floer himself, he developed this Floer homology to really try to understand periodic motions in Hamiltonian dynamics. Same thing with Morse-Conley theory. Lots of beautiful theory have been developed to actually really try to understand solutions of nonlinear equations. Same thing in, Poincaré himself, he developed the basis of algebraic topology to try to understand periodic motions also in celestial mechanics. So a lot of these beautiful pen and paper analysis techniques have been developed trying to understand solutions of nonlinear equations. So that's I would say, the pen and paper analysis tower. And then on the other hand, you have, which basically is probably more the focus of this workshop, you have the very powerful and beautiful techniques and tools coming from scientific computing and numerical analysis, approximation theory, to simulate numerically solutions to these complicated equations. And I felt like traditionally in my career and in my studies that these worlds were often quite separate, and the people from the left tower will look down on the people from the right tower, and vice versa. And I never felt comfortable in this world of fighting. And what we propose, and the kind of feel of computer-assisted proofs, is kind of an attempt to build a bridge in between these two worlds. And of course, the bridge may be very tiny, but hopefully it's going to keep on growing as time evolves. Okay, so what do I mean by computer-assisted proofs in dynamics? I mean, the way I see it is as follows. So the idea is to construct some algorithms that provides an approximate solution to a problem. And then we want also efficient bounds and precise, so that we can have a mathematical theorem that says that, close to a numerical solution, there is just a true solution to the original nonlinear equation. And this field really draws inspirations from different math fields like scientific computing. Yeah, you see them here, but it really is a blend of these fields. And it's important to mention that what I'm talking about today is by no means new, and then it goes back all the way to Césarine 1964, where you actually use a computer to prove existence of some periodic motions in a very simple, I think it was a second order non-autonomous ODE, and use somehow very similar ideas that I'm describing today. Of course, now we have much more experience and much more, there's much more machinery, both from nonlinear analysis and scientific computing. So now we can push the results much further. But yeah, so I don't see, okay, yeah. Yeah, maybe let me just mention also the pioneering work of Lessard in 1982 about computer-assisted proofs of the Feigenbaum conjecture. So the pair doubling bifurcations in the logistic map. So he proved these conjectures using the computer, a fixed point argument, and series expansion. And Marian Morozek and Konstantin Mishakov in 1995 proved the existence of chaos in the Lorentz equations using computer-assisted proofs. And 1999, Warwick Tucker proved the existence of the Lorentz attractor. And that was basically solving one of Smale's problem. It was a pretty big deal. And there's a lot more results of computer-assisted proofs in dynamics. I'm not going to discuss much about the history, but I want to give you the flavor of at least the approach I am taking. And our group is taking in this direction. So our approach is functional analytic, and it uses ideas from nonlinear analysis, and of course it uses a lot of ideas from numerical analysis. So I want to present that briefly. So now I'm completely outside Navier-Stokes, so now I'm considering a non-general, a general nonlinear problem of the form f of x equals 0. It's posed in a Banach space, okay? And the unknown could be many different things. Here's a list. And of course, I am interested in dynamical systems, so I'm interested in these so-called bounded solutions, so periodic motions, connecting orbits, critical points, steady states, bifurcation point. Yves mentioned that at the beginning. We can prove existence of bifurcation points using these techniques, but for the sake of this talk, you can think of X as being, say, the Fourier coefficients, the space-time Fourier coefficients of a periodic motion in Navier-Stokes. I will be more explicit about it, but just for the moment, you can think of X, the unknown to be found, to be representing the periodic motions in Navier-Stokes. Okay, so we have a general nonlinear problem which we want to solve in a Banach space. Okay, so it's nonlinear, so there could be a lot of different solutions. In fact, there could be infinitely many solutions. Again, if you think of the Lorentz equations, for those of you who know the Lorentz equations, then it's a three-dimensional ODE. And if X represents periodic motions in the Lorentz equations, then it's known that in the global attractor, there are infinitely many periodic motions of arbitrarily large periods. So if X represents the periodic motion, then there's a lot of them. In fact, there's infinitely many of them. So it's impossible to compute exactly. And not only it's impossible to compute exactly, but these are functions. If you think of a periodic motion, it really is living in the function space. So also to represent the solutions, it's quite hard, right? Because you need to take a finite dimensional representation and so on. So it's a highly non-trivial task. So what do we do instead of computing them exactly? What we propose is to find small balls in which it is demonstrated, and by demonstrated I mean in a mathematically rigorous sense, that a unique solution exists. Okay, so how do we find these small little isolating balls? So we first have to compute an approximate solution. So say I have an infinite dimensional problem. So I take a finite dimensional projection. It could be a Galerkin projection. It could be a projection coming from finite elements. But it takes a finite dimensional reduction of the problem, and we solve numerically the finite dimensional projection. Okay, so again, it could be by using Newton's method. It could be by using a continuation method. It could be using any kind of method that you want, hopefully with a high enough accuracy as far as the finite dimensional reduction problem is concerned. So that's the first step. So that really requires choosing a basis, choosing tools from approximation theory, choosing the right finite dimensional reduction. And as I said before, so if we are after, say, periodic motions and we represent them using Fourier coefficients, then the regularity of the solution implies fast decay of the coefficients, which we can then use in our finite dimensional reduction, because the hope is that a finite dimensional reduction will actually capture the essence of the solution that we're trying to prove for the infinite dimensional problem. So that's the first step. And once we have this, then the goal is to actually try to prove that close to the numerical solution, there is a true solution by applying a contraction mapping theorem close to the numerical solution. And the contraction mapping theorem is often nicely verified by a Newton operator. And a Newton operator, as we all know, requires computing, say, the inverse somehow of a derivative. So, but in infinite dimension, this is quite hard. So rather than computing the exact inverse of the derivative, what we do is that we first use a computer to construct a linear operator that acts as an approximate inverse for the Frischet derivative of f at x bar. So here, this is really the infinite dimensional Frischet derivative. Yeah, I will show you how to do that in Navier-Stokes in details later. So that's the second step. And then after that, we verify that A is an injective linear operator. Why? Because we want to define the Newton-like operator. And if A is injective, then the zeros of f, which are providing us the interesting solution that we want, the zeros of f are in one-to-one correspondence with the fixed points of t, provided A is injective. Okay. So the fourth step is to define a Newton-like operator. And then we consider a ball of radius r centered at the numerical solution. So keep in mind, x bar is the numerical solution of some a priori unknown radius for which we're going to solve. And the goal is to find a positive radius. So basically the ball about the numerical solution such that T, the Newton-like operator, is a contraction. And by the contraction mapping theorem, T contains a unique fixed point in the ball, and then therefore A has a unique fixed point, A has a unique zero in the same ball. And then we have our exact solution, which lies within a radius, a ball of some prescribed radius r, which again, we have to solve for. Okay, so let me be a little bit more explicit about how to show that we have a contraction mapping for T. So here's the theorem, which is very much in the spirit of a Newton-Kantorowicz type theorem. I'm going to denote it. I'm going to be a little bit more explicit about it here. So let's consider T our Newton-like operator. And then we assume that T is C1, which is going to be the case if F is C1. And then we consider R positive and two bounds. So let's say I have a bound, which I call epsilon here, and it's the numerical defect. So it's basically measuring how far the numerical solution, which I computed again prior to this whole process, it sits on the memory of my computer. And so I want to measure how far the Newton-like operator maps the fixed point from itself. So I have to choose a norm in my Banach space. I will again present you all of that in Navier-Stokes later, but that's for the moment, this is general. And by construction of the Newton-like operator, this is nothing else than the norm of A times F of X bar. We want to verify with the computer that this is less or equal than epsilon. We basically compute this number with interval arithmetic and with the representation that we have of this problem. And then after that, we compute a second bound, which is denoted by kappa of r, and it is nothing else than the Frischet derivative of the Newton-like operator on the same ball. And by design, then this is nothing else than this quantity here, which is the operator. That's really is the operator norm of the identity minus A times the Frischet derivative of W, where W is taken in the ball. So I denote this bound by kappa of r. It depends on the radius, because if you think of that, then when you take the radius larger and larger, then that's going to be increasing the number, right? So, and if you had perfect Newton, if it was perfectly equal to the inverse of the derivative, then it's not hard to convince yourself that when r goes to 0, then that quantity goes to 0. So there is hope that kappa of r for small enough r will be less than 1. So the theorem says that if epsilon plus r times kappa of r minus r is negative, then T is a contraction with Lipschitz constant kappa of r less than 1. And therefore, by the Banach fixed point theorem or the contraction mapping theorem, then F has a unique 0 in the ball. Okay, so if you look at this quantity here, then you can see that when you plug r equal to 0, then that's not going to work, right? So because basically epsilon is not less than 0 unless you had a perfect, and unless your numerical approximation was exactly a 0 of F, which is obviously not the case. So this positive number here limits how small you can take your radius. So you cannot take it too small, and it makes sense because if you think about it, if you think of x hat as the true solution to your problem and x bar to the numerical solution, then there is clearly a distance. So if you take the ball centered at x bar, your numerical solution, too small, which corresponds to taking r here too small, at which P of r is not negative, then you do not have a unique solution. You do not have an enclosure. And if you take it too large, then Newton may just not be a contraction anymore, or you may have two solutions. So then there's the sweet spot, right? So that's basically why we solve for the radius for which we can prove contraction. But in practice, I mean, these bounds, we kind of compute this with interval arithmetic and with the help of the computer. And this bound here we use tools from functional analysis, nonlinear analysis to actually get estimates, analytic estimates, together with computations to compute this polynomial in R. That really is a blend of computing and analysis. Okay, I can see that there is a question. Your epsilon. Is there a way to ensure that the solution is inside your epsilon radius bound? So in practice, the epsilon here is the numerical defect. So that the radius will not be quite equal to epsilon. It will be bigger than epsilon. But in practice, we have this recipe, right? So we construct all the bounds, and then we will find a positive R for which it is negative. So we will have a strategy to compute this radius, which is not too small and not too large. So I'm not sure if I answered the question.
Yeah, that's perfect. Thank you.
Okay. All right. So now I'm going to jump back into the world of Navier-Stokes. So I talked more generally about the approach, and now I'm going to apply this approach, this general approach to the Navier-Stokes equation. So this is joint work with Jan Bauer van den Berg, Maxime Breden, and Leonard van Veen. And all right, so the first part is to actually design a zero finding problem. So I mentioned this f of x equals 0. So that's the first step that I want to introduce, okay? So rather than working directly with Navier-Stokes, what we do is that we apply the curl to Navier-Stokes and we work with the vorticity equation. Okay, so then we're going to be solving for the vorticity, so the curl of the velocity. And in that case, the external forcing term becomes also the curl of the forcing term. And the linear terms, they don't change, but the nonlinear terms are going to be affected by that. And what we do is that we plug the space-time Fourier expansion because, okay, it's very important to realize that I'm focusing on the 3 torus. Okay, it's a big restriction. There are many people from scientific computing and engineering in the crowd, so I do acknowledge that this is limiting in the sense that we are having a cube. I mean, it's a 3 torus, right? So if we wanted to use more complicated geometries, then we would have to change basis and we would not have the luxury of being able to use Fourier techniques. But yet there are people in this field working with non-rectangular domains, and then they're using something very similar, this Newton-like approach, but now using finite elements. That's a possibility. Well, what I'm presenting today is not with finite elements, it is with Fourier, which comes from the fact that I'm taking Navier-Stokes posed on the 3 torus. Okay, so once you accept that, then what we can do is that we can expand the vorticity as a function of, I mean, the 3-dimensional spatial variables, x, and then the 1-dimensional t, as Fourier series, because keep in mind that our goal is to find periodic motions. So it's going to be periodic in space because we are in the 3 torus, and it's going to be periodic in time, but it's going to be periodic in time with some unknown period. So here, omega is the frequency, it's equivalent. I mean, it's 2 pi divided by the period. So this is an unknown that we have to solve for. Again, here, the 3 torus, I assume that it has width 2 pi. So what we do is that we plug that space-time Fourier expansion in the vorticity equation, and that results in having to solve infinitely many nonlinear equations defined by Fn. So here, instead of x, it's omega, not the unknowns, w, sorry. So once I plug the vorticity in Navier-Stokes, in the vorticity equation, that's in Fourier, that's the corresponding term corresponding to the time derivative. So the time derivative has I and 4 omega, and the corresponding linear term in Fourier for the diffusion is this one, and that's the Fourier coefficient of the external forcing term. And then still I have some nonlinear terms, which I'm not going to put there because they're coming from the advection. So you apply the curl to the advection. So you have 2 terms coming out. It becomes a little bit technical to write them down, but we can put our hands on them. That's not a problem. And here the frequency is unknown, as I said, and n tilde is just a notation for n1 squared plus n2 squared plus n3 squared. So again, we have 4 indices. We have n1, n2, n3 for space, and we have n4 for time. Okay, so that's there's a lot. There are a lot of unknowns. So the unknowns are the frequency and all of the non-zero Fourier coefficients indexed over Z4. So that's a very high dimensional problem and quite nonlinear. So that's really is, when you think about it, this problem here is really an infinite dimensional nonlinear problem. Okay, so that is going to lead to this f of x equals 0, where x again is W. And here's the justification from solving f equals 0 is that if you have W such that f of W is equal to 0 and the curl of the divergence of W or of omega is equal to 0. And if f does not depend on time and has space average 0, then when you define u to be a solution of omega equals the curl of u, which is possible to do, it's actually very, very explicit solution to that in Fourier, then there exists a pressure function and there exists a u, which is this one, the u solving this equation, such that up is a 2 pi over omega periodic solution of Navier-Stokes. And in fact, we will do a computer-assisted proof to find the W, and the computer-assisted proof, the rigorous error bound that we will have, will also give us a direct rigorous or upper bound for the location of the velocity. So we'll have really a explicit control over the velocity periodic motions in the original Navier-Stokes. But now we focus on solving f of W equals 0, where W corresponds to the Fourier coefficients of the vorticity. Okay, and the only thing that I did not mention is that we want to apply contraction mapping theorem, and in that context, periodic motions in time are not isolated in Fourier because every time shift of the periodic motion is still a periodic motion. Because of that, that means that there's no way to actually get a unique solution locally, which is kind of the whole philosophy of what the approach is, that is to prove existence of a contraction in a small ball. So in order to eliminate time shifts, we impose what we call a phase condition. It could be a Poincaré phase condition. So here I have written down an integral phase condition, which basically eliminates time shift of the periodic motion. So once this is done, then I design this new f equals 0 problem, which includes the phase condition, which compensates for the fact that I did not know the frequency. So that balances for the frequency. Always 0 if omega is analytic. The divergence of omega always 0 if. Right, but here we don't. So once we solve the vorticity equation, we don't assume that omega is the divergence of something. We just solve the right. We just solve the vorticity equation, and then we do not assume it's just really at the end that we will get it. But okay, right, okay, all right. So this is now the zero finding problem that I mentioned. Okay, so the first step, to go back to the general picture that I had in terms of the steps in order to solve the nonlinear problem, is to identify a Banach space in which we'll solve and to find numerical solution and so on. So the Banach space on which I'm going to solve for f is the following. So keep in mind that we have 3 components because the vorticity has 3 components. You can call it W1, W2, and W3. And each of these components is represented by infinitely many space-time Fourier coefficients. Okay, so for each of these components, we define this weighted L1 norm, weighted L1 space, which is in fact a Banach algebra under this discrete convolution. So Banach algebra is nothing else than a fancy word to say that when you have a Banach space with a norm and you have a product, and in that case, the product is discrete convolution. So it says that the norm of the product is less or equal than the product of the norm, nothing more. So it's actually not quite difficult to show that if you have, say, 2 Fourier series, you multiply them together, then their coefficients are discrete convolutions. And this discrete convolution under weighted L1 norm leads to a Banach algebra, okay? And basically that's it. So that's, the weighted L1 norm is the following. So you take the sum of over all n in Z4, minus the zero element, of the absolute value of the an, and then I have this eta, which is a number greater or equal than 1 to the power n1 plus n2 plus n3 plus n4 in absolute value. So that's basically this. Oh, sorry. Okay. This quantity here is the, actually, I don't know. Do you see my cursor?
Yes, we do.
Okay, thank you. So this number here is, if eta was equal to 1, then that would just be L1, okay? But, okay, so then the Banach space, since we have the frequency is an unknown and the three components of the vorticities are unknowns, and I take my Banach space to be the product of C cross 3 copies of L nu 1 with that norm. So that's the L1 norm of the L1 norms, okay? So that's my Banach space in which I'm going to look for zeros of F. And the fact that I chose this weighted space is that, for instance, if eta is strictly greater than 1, then an element of L eta 1 is going to be, in fact, a sequence which will decay geometrically fast to 0 at infinity in all 4 directions. And that choice is based on the fact that in the Navier-Stokes equation, bounded solutions in periodic motions, if they exist, then are going to have very fast decaying Fourier coefficients. And then you can see that by actually bootstrapping, okay? So this a priori knowledge of regularity of the solutions, if they're there, is encapsulated in this choice of Banach space, okay? So now we have identified a zero finding problem and a Banach space in which we're going to solve for it. Yes, we could numerically solve Navier-Stokes without transforming it into the vorticity equation. So the reason why we did this is that our formulation relies on computing a good approximate inverse of the derivative, okay? And if you keep the original Navier-Stokes and you have to solve for the pressure, then you'll have, in the whole formulation in Fourier, you'll have some blocks which will not be diagonal dominant, and that made our life very hard actually to be able to kind of get our hands on a good approximate inverse, because basically one of the ingredients that we use is that the Frichet derivative is a diagonal dominant operator, and that was not the case in the original Navier-Stokes equations, okay, because of the fact that we had to solve for the pressure, and we were struggling for that for some months, and then Leonard van Veen from UOIT said, well, anyhow, the engineers often are solving for the vorticity, and if you really care about the velocity, then you can recover it by solving, U equals the curl of W. W equals the curl of U by the inverse problem. So he said, not only it's going to be cheaper to compute, but from our perspective, it's also the fact that when trying to prove something about the original Navier-Stokes, we did not have the nice structure that we wanted. So that was, for us, it was kind of necessary. But of course, we could numerically solve Navier-Stokes directly without transforming it. But for our perspective, to do the proof, because of the lack of diagonal dominance in the Frichet derivative, which I hope will become clear soon, then we did not manage directly in Navier-Stokes. So that's why so I hope it answers the question. Okay, so what we did, so we considered an external forcing terms to be the following. So that's the external forcing term that we have. It's a time-independent forcing term, Taylor-Green. Let's see if it, okay, good. So we took a Taylor-Green time-independent forcing terms, and then we applied the curl to the forcing term. And then that's for this specific forcing term that we applied our approach. And in that case, there is a viscous equilibrium, the one that I talked about, the one that Seren proved, that for large viscosity, you have a viscous equilibrium. And in this specific example, because it is Taylor-Green, then we have an explicit formula for the viscous equilibrium. And from that, we did a continuation, and then we computed some numerical periodic motions using continuation. Okay, so then we did all of that for Navier-Stokes, and now I want to give you a bit more details for the approximate inverse. I don't have a lot of time left, but I'm going to give you at least an idea of how to do that. So we want to compute so that we can define a Newton-like operator. We want to compute an approximate inverse for the Frischia derivative of f at an approximate solution W bar. So if you keep in mind what f is, so most terms are this. So this here is a diagonal term, and these are nonlinear terms. These are coming from the advection or the curl of the advection term, and then in Fourier, they correspond to discrete convolutions. But because they come from discrete convolution, and because W bar is in fact decaying, because it's a sequence of Fourier coefficients with some decay, then the actual off-diagonal terms, they tend to zero as we get away from the diagonal. Okay, so that's the diagonal here, which comes from when you take the Frischia derivative. And here I represent the finite dimensional Jacobian matrix of the finite dimensional reduction at the finite dimensional approximation. So I would say that that's the real structure of the Frischia derivative at the approximate solution, which has only finitely many non-zero modes. So what we do,
5 minutes.
Yep, 5 minutes, parfait, parfait. Oh, je vais avoir le temps. C'est bon. So what we do is that we approximate the Frischia derivative by just this. We say, well, these terms are converging to zero. So then I can just say that but I first approximate the Frischia derivative by this, saying that this is diagonal dominant, and then I can just neglect these terms. And again, keep in mind that we are going to apply a contraction mapping theorem, and contraction mapping is flexible in the sense that if you have small errors or if you do approximations, and it's a topological argument, so there is room for errors. Okay, so I approximate first my derivative by this, and I say, well, now I'm going to use the computer to compute numerically an inverse for that finite dimensional Jacobian matrix, which is very large dimensional for us. I mean, yeah, maybe it's 40,000 by 40,000 or slightly bigger. And then we compute a numerical inverse, and then we plug that in the finite part, and then we invert the tail by hand, and then that's my approximate inverse. Okay, so that really is a computer-assisted approximate inverse. That part will sit in the memory of the computer, as it is the case for the numerical solution. So now I have this operator A, which acts as an approximate inverse. Now I can define this Newton operator based on this approximate inverse, which is computer assisted. And then I can now go back and say, well, I'm going to apply and compute now these bounds, the bounds from the Newton-Kantorovich theorem to show that we do have a contraction. Okay, so this is what we did. Okay, right. So at this point, we have W bar, we have the Newton-like operator, we have the approximate inverse. So we have to compute these bounds. And these bounds are now really going to be computed using the power of the two towers that I mentioned before. So say the first one, so we use interval arithmetic, which makes sure that all the floating points errors when you compute products, when you do products of matrices by vectors, when you take discrete convolutions and all of that, then these are all the floating points error involved in that these computations are rigorously controlled. The kappa of R we use, I don't give you details, but we use tools from nonlinear analysis. We use the Banach algebras that we have to compute quantities, which in the end we will be using the computer to compute rigorously with interval arithmetic. But really from the left tower, we use tools from nonlinear analysis, functional analysis to compute these bounds. And then we use, of course, approximation theory, numerical linear algebra, scientific computing to compute numerical solutions, to invert the matrix, and then to use, we use fast Fourier transform as well together with interval arithmetic to verify that there is just a positive R for which this is negative. So at this point, you can really appreciate that this is really a mix of the two worlds, that we really need the two worlds to actually do something about computer-assisted proof. Okay, and in this case, we used 2 minutes. We used IntLab in MATLAB to do the interval arithmetic. So a couple of more slides. So let's say this is the viscous equilibrium. There is a half bifurcation. So we computed two solutions, and then we proved their existence using the computer. So I'm going to show you a movie of P2. So this is P2, a periodic motion, which was proven to exist in Navier-Stokes using the tools of computer-assisted proofs. And that paper just appeared. That result just appeared in the Journal of Nonlinear Science. And basically, the rigorous error bound that we got, so 10 to the minus 6 away from this periodic motion, there is a true periodic motion that exists. Okay. And maybe one thing I can say is that in that diagram, then there is a period doubling bifurcation, and then there is a three-dimensional orbit that comes out. So this branch here is kind of two-dimensional in the sense that the forcing term is two-dimensional. So the birth of periodic motions here are two-dimensional, but there is a truly 3D one that we are working on right now, and then we are trying to get our hands on it. And now all the estimates are done, but we do not have yet the power, the computational power to do this. So we're trying, instead of moving to a cluster or to a high performance computer, we are trying to use more the math to actually reduce the computational time and then reduce the number of Fourier coefficients. So this is work in progress. All right. So I guess I'm out of time and I'm not going to talk about that. And I will just thank you all for your attention.